Derivatives of functions from first principles, an introduction. The derivative of a function is the gradient of a curve. For a straight line, the gradient doesn't change. We can calculate it from 2 points like this. The gradient equals rise over run, or y2 minus y1 over x2 minus x1. These 2 points are on a straight line graph. You can see from the graph that anywhere along there, rise over run is the same value, 1. For a curve, the gradient depends on the value of x and is the same as the tangent to the curve. You can see the tangent changing here as x changes. The problem with curves is that the tangent only has 1 point on the curve. How do you get the rise over run from 1 point? The answer is to sneak up on the answer. We start with 2 points and bring them closer together so we effectively end up with 1 point and the tangent. This graph for a curve shows the actual tangent we want to calculate the gradient of. It's the green line. Now I have added a secant line which has 2 points. Its gradient is equal to what's shown below. The two lines have different gradients. However, as h decreases, the gradient of the secant gets closer to the gradient of the tangent. When h equals 0, it would be perfect. However, if h equals 0, the gradient is undefined. To solve this problem, we take a limit, which means sneaking up on the answer. The derivative of a function is defined like this. It is the gradient of the secant as h goes closer and closer to 0. Let's do an example. In this example, the function is equal to x squared. To calculate the gradient, we need to also calculate function x plus h, which is equal to x plus h to the power 2, and expands to x squared plus 2xh plus h squared. Here is the formula that we use. We substitute in fx plus h and fx, and we get this. If we simplify by collecting like terms, we end up with this expression. We can simplify the fraction by dividing the numerator and the denominator by h, which we can do as h is not equal to 0. If h was equal to 0, this step would be invalid. To finish this off, we let h approach 0. You can imagine it is some small value like this, or as many decimal places as you care to imagine. As h approaches 0, the derivative function approaches 2x. I can use this new function to find the value of the gradient for any value of x. For example, the derivative when x equals 1 is equal to 2. The derivative when x is equal to 0 is equal to 0. This is the way to calculate the derivative for any function. In real life, we notice there is a pattern and we use a shortcut method. Thanks for listening and watching.